Saxon Algebra 2, Lesson 113. Greetings, my students. Today we're going to begin a lesson that is more of a head game than anything else. We're going to take something that we've studied extensively and that you're very familiar with and that I know you know how to handle really well. And we're going to kind of turn it upside down and inside out and put some new names on things. And John's going to try and confuse you. I have bet substantially that you're not going to fall for his game, that you'll be able to see through the layers of confusion and realize that this is not anything new. So let's dive in. The topic is logarithms. Logarithms were really important back in the days when people used these instead of calculators. Look, it's my husband's all-metal slide rule from when he was a 1960s engineering student. Someday I'll take it all apart and show it to you, but look, it's right here. It sits by me every night when I record my lessons. It's a slide rule, and slide rules work on logarithms. So it used to be a really big deal that mathematicians had to understand logarithms. It's not as much for us, right? Because we have calculators, but they're still important, and the well-rounded math student needs to know logarithms to this very day. So here's the thing about logarithms. They are equal to or same as exponents. If you understand exponents, you'll understand logarithms, because logarithms are just an upside down and inside out way of looking at exponents, okay? But you understand exponents, so this is not going to be that hard. So let me show you something that you know, and you're going to be like, okay, she's completely lost your mind. This is not even anything new. 10 to the third power equals 1,000, right? You know that because we know we can do that in our heads, right? Because any power of 10, you just add up the number of zeros as there are exponents. So there would be 3, blah, blah, blah. Let's call this the number. It's the number that you calculated. And let's call this the exponent. Oh, that's clever, right? Or we could call it the power. Sometimes we call them that. And this number we'll call the base, right? We've been calling those numbers that forever, right? The thing that gets an exponent put on it is called a base. Okay, cool. When we talk about anti-logs, we're going to give these things some new weird names. We're going to call the exponents, logarithm. It's an exponent, but we're just going to call it a logarithm or a log. And here comes, I mean, it's weird, right? Like, why did we make this so hard? Don't let it mess with you. The number, oh my gosh, you guys, this is the one that makes me want to cry, is called the anti logarithm. What in the world? That's sick, isn't it? But it's just its name. And the base stays the base, but there are two bases that we're going to use a lot. The first one is base 10. Well, that's base 10. We're used to that. That's easy. The other base is a base that is, let's see, what's the best way to explain it? It is a base that is used for a lot of calculations that have to do with physics and engineering. Okay, it's a base called E. It's kind of like pi, you know, we call pi, even though it's a number that relates to circles. We just call it pi. This is the number we call E, so that's what we call it. And we say natural log, okay? We can say E, but we can also say it's the natural log. And the number is 2.71828. Yes, we usually round that, okay? What's cool about these two bases is that they are programmed into your computers, your handheld calculators, I should say, which is a computer. But these are the two most common bases. We can use other bases, but these are the most common ones. And so we're going to use those, and they're all loaded into your calculator. You don't have to use tables in the back of your book like I did back in the days when the dinosaurs ran free. But those will be the most two common bases that we use. Most students find E kind of confusing at first and think base 10 feels really comfortable. That's fine. We'll lean into these problems and just trust me, with a little bit of time, this will feel more common. Okay, so this is all information you know. Other than these weird new names, you get it. The way that we write this is called an exponential equation because we've written it in exponent form. Okay, so that's what this is called. We can also write this same thing as a log equation, which is log 10 of 1,000 equals 3. What did I just do? I took something so simple and I turned it into a freak, didn't I? But look, here are all the numbers. 10, this is the base right here. Oh, this is the number. Or if we want to be weird, we can call it the anti-log. We don't usually say the logarithm, but we can say it's the anti-log. And then this number is the exponent or the power. But we can also call it the log because we're cool like that, right? It means the very same thing. The way we look at this is that the exponent we put on 10 to get 1,000 is 3. It's the same information, just inside out and upside down. Now, students a lot of times get freaked out on logs, especially as we go a little further and learn some new things to do with it. Students will get freaked out. I always come back to this. If you can write out that and then translate it into that, it helps you just get your head back in the game and remind you, oh yeah, I really do know all of this, okay? So that's the basics of what I want you to know. Now, like I said, working logs is kind of fun because you can use a calculator, all right? Now, here's the problem I have. My calculator is currently pulling double duty as a high-tech video camera in my studio here. So here's what I've done. Don't worry about this part. Just look at the buttons. Those are the buttons on your calculator that you need in order to do this. I just use the calculator on my phone. Get one of the kinds of calculators that has like basic functions if it's in portrait, but then when you flip to landscape, it's the same one that you'll be using for trig functions, that you've been using for trig functions. So you should be able to find 4 buttons that look like this. They're always together in this arrangement, okay? And we're gonna learn how to use these buttons to work these problems, all right? And what John is choosing to do is start us out with some calculations I'm going to start slightly out of order, but it's going to help us understand what logs are good for. So let me move this piece of paper out of the way. Have your calculator handy is what I wanted to tell you. And I want to start with problem 2. Use base 10 logarithms to simplify. Okay, that's cool. Base 10 is what we like. It's in the calculator. That's all cool. And then what John does is he gives us 3 numbers. 4, 47, 832. Okay, he wants us to simplify this. We're kind of used to doing this as scientific notation, right? We're used to doing that. This log calculation is going to look a little different, but it's kind of theoretically the same. Let's get through it and then I'll explain to you. So what we want to do is we want to write each of these numbers as a power of 10 to the something. That'll be this one. And then this will be 10 to the something. That'll be that one. And then this bottom one will be 10 to the something too, right? We don't know what these exponents should be yet. And then we'll be able to use the product rule and the quotient rule to simplify, right? Our old friends. Let's just write them down. Plus n. There's the product rule. Oops. Those are both x's. There's the quotient rule. And there's the product rule, which we won't need for this problem, but I'm just writing these down. There's nothing different here. These are just the rules for exponents as you've known them for years now. So what we're trying to do is we're trying to rewrite this number as 10 to a power. Now, I don't know how to do that in my head, and it's not like we did for scientific notation, because there we just bump the decimal and say multiply it by 10 to a power to move that decimal back. This is different. It kind of looks the same, but it's different. What we need to do is say, what is the weird exponent that you put on 10 and multiply it to get 47,832? I don't know what that is. That's a really random number. Okay, grab your calculator. We know the number that we want to get, and we know the base. What we don't know is the exponent that we want to put on that, right? So look what we do here. These are the buttons. Let me cover up the ones I don't want. Okay, let me just show you this though. These are the base 10 buttons, up and down. These are the base E buttons, the natural log buttons, up and down. Right now we're working in base 10. So we know that we don't need the natural log buttons, right? So I'm just going to get those out of the play. Now I wrote over here what the two rows are good for. And these explanations work for the E buttons as well. Write this much down right now. Draw yourself a button, 10 to the x. Draw yourself another button, log 10. And write underneath it base 10. Okay. This is the button we use when we know the exponent, or log, and we want the number, or anti-log. I hate to say anti-log, so I'm not going to say it. But this is when we know the exponent. So if I wanted to find out what's the power of 10 to the 0.5716, I could plug in 0.5716 and find it. We don't want that either. We don't know the exponent. In this case, we know the number we want, 47,832 or whatever it was. We need to know what the exponent is. So this is the button that we want to use for this calculation. All right. We know the number. We need the exponent, or log, whichever word you prefer to use. All right. While you're at it, let me have you calculate the rest, draw the rest of this so that you have this in your notes so that you can keep this forever, you guys, because no matter what kind of problem you have, this will always be true. This is the base 10 column. This is the natural log column, but then these descriptions work this way. It's kind of like a chart, right? So if you know the exponent and you need the number using the base E, that's the button. If you know the number and you need the exponent, I keep saying it, I know it's probably driving you crazy. Just copy this, I'll give you a minute. And then when we have a problem, I'll refer to this picture, since I don't have a calculator. Okay, so we want to find the exponent you put on 10 to get that. So I grab my calculator. I know the number. I want the exponent. It's base 10. That zips me into this button. I enter to my calculator 47,832. Then I hit that button, and I should get 4.68. Cool. Now I do the same thing. I enter 59,463 and I hit, once again, same button, log 10. I know the number, I want the exponent. That time I should get 4.77. My boxes are too small. And then I enter 0.000817, hit the very same button, this one, I know the number, I need the exponent, and that gives me minus 3.09. Makes sense that it's minus because that's a decimal number, right? Okay, now I'm ready to use these rules. So I can take the exponents off and I can say 4.68 plus, because this is product, 4.77 minus, because this is quotient, so now we're going to subtract, but it's already a minus. All right, so I add those two, I subtract that one. It happens to already be minus, so I'm going to be adding all that schnizzle together. And I get 10 to the 12.54. Beautiful. That could be the answer, or we can take it back to our calculator. Again, we're still working in base 10 only, but now I know the exponent and I want to know what that number is when I multiply it out. So this time, I want to use that button. I know the exponent that I'm putting on 10. I want to know what the number is when you multiply it out. So I enter 12.54. I hit that button, and the answer that I get is 3.47 times 10 to the 12th. Now, sometimes this will freak a calculator out, so that's why I don't mind that. But this is the best answer. Notice that we've written it in scientific notation, but logs, even using base 10 and scientific notation, are not the same thing. I don't want to get into a big conversation about how they're different, but they're not the same thing. All right, that is a super great explanation of what logs are good for. Right? Now we think, well, why would we do all of this when we can just enter this into our calculator and do it? Because there was a time when we couldn't just enter these into a calculator and we needed to use slide rules to figure out calculations, and slide rules are all based on logs. Okay, let me go loop back to example 113.1 because this is a good need to know. It says use your calculator to get a value for E. This is a good question because everybody forgets the value of E. We know that pi is 3.14, right? But it's really hard to remember. Where did I write it down? On this other page. I'm looking for it. The value of E. Oh, here it is. I told you here that E is 2.71828. No one remembers that the first time they hear it, right? So what if you want to know what the value of E is and you don't have it in front of you? If you've got a calculator, you can always find it. Because what you can do is, we know we want to zoom in on the E button, so we ignore these, right? We know we want the number that this is equal to. So what we do is we just let the exponent equal 1, right? Because anything raised to the first power is the same. So you enter 1 on your calculator and then hit E, and you will get, so we want to use the E to the X button. And that will give us the 2.71828, la da 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 da. It is an irrational number. It has infinite non-repeating decimals. All right, so that's the answer for this one. So that is a great hack If you ever need the value for E and you can't remember it, just grab your calculator, put in an exponent of 1, hit that button, good to go. Okay, let's move on. And we have 3 more problems. I'm sorry. Use base E logarithms. Okay, we're going to do that same problem again. I'll copy the number down again. 47. We're going to use these very same numbers. 59, 463. Divided by, I think it was 30817. Yes, that's right. Okay, this time we're going to use the values for E. So the first number we want to change it so it's E to the something exponent times, I'm making my exponent boxes bigger this time, E to the something exponent over E to the something exponent. And then we'll be able to do the same thing. We'll be able to add and subtract for the bottom number, and then come up with a final value that will be E to the something, and then we'll express that as an actual number. All right, so here's our calculator. Here's my calculator. It's like, you know how when little kids like use weird things for cell phones, like they pretend they have a cell phone, but it's really like, you know, a box of butter or something. That's what I always feel like when I do this. It's like, this isn't really a calculator, but I'm pretending it is. Okay, this time we know we want to have these values. I wish I had something that proper size. I'm looking around me. I'll do this. Hang on, I'm doing a little origami on the side. I'm sure you are too, right? One of my daughters, my youngest, loves origami, and it helps her focus and concentrate. So whenever we go to church, whatever that is, during the message, she always folds origami. Okay, ready? Here we go. So we don't need base 10. In this case, we know the number and we need the exponent. So again, we're going to use this box. Remember, this stands for natural log. It's log natural. I don't know why it's reversed order. I can't explain that to you. But this is the button we use when we want to use the base of E, the natural log, and we know the number, but we need the exponent. So just like before, you're going to enter 47,832 and then hit this button. Okay? It's going to say, hey, that's the number. Give us the exponent that belongs on the base of E to get that. And what the calculator will tell you, I hope you're trying this and making sure it works. This is 10.78. Then we do the same thing. You enter 59, 463, and you hit again that LN, that natural log button, and you will get 1099. And then this will be minus 7.11. Okay? The calculator does all that heavy lifting for you. Then we just use the product rule, and we do 10.78 plus 10.99 product rule, and then quotient rule, subtract minus 7.11. So we're actually adding that, and the number that we will get is 28.88. Those three added together should be 28.88. Now we know the exponent that's sitting on top of our base. We want the number that it represents. So this time we flip up and we use this one. We know the exponent or log, and we need the number. So this is the one we want. We enter 28.88 and we hit that E to the X button, and we get 3.49 times 10 to the 12th. Again, that's scientific notation. That's different than a log, but this is our answer. And if we played our cards right, it should be the same as last time. 3.47. So it's, oh, that shouldn't be. Let me make sure I didn't copy that one. If you do it right, it should work out exactly the same. Oh, our answers are different because of errors that accumulate when we round logarithms. So that's good to know that the more decimals you put into your exponents, the more accurate your answer will be. That's close enough for our purposes to show you how these work, but it's a good heads up to you that pulling out some more digits is going to be super helpful in increasing the accuracy of these calculations. As I was going to say, as if you care. That wasn't very nice of me. Okay, if minus, these problems are shorter. We have 2 more and then we're done. Okay, here we have this impossibly difficult looking thing. Find y, and then this. Dear God, what does that even mean? I don't even know. Well, I do, but I can imagine you saying that. It looks confusing, and that's when we need to pull back to our basic plan here and go, okay, this is how a log equation works, right? That's the base, that's the number, and that's the exponent or log. Okay, that's what this is. It's just written in the opposite order. Let me rewrite it just to help you see it. So our base is E, so we know which row of buttons to use on the calculator. This number represents the exponent, or the log, and this is the number, right, that we get when we put it on. And we also call that the anti-log. John's really big into using that phrase. It just annoys me. So we can rethink this. Just the way we can write that as that, we can say that E to the 0.0325 equals y, right? Because that's the base, that's the exponent, base, exponent, and then this is the number. So what I did was I inside outed and right side arounded, and I came up with something that feels more natural in my brain. This is the log equation, this is the exponential equation. This I can do in my calculator quite nicely. I'll enter, here, let me just scoot it up a little. I'll enter 0.0325, I'll hit the minus, then I will use this button because I know the exponent and I need the number, and I will get 0.968. And that means y equals 0. Second, I want to make sure I'm copying it. It's 968. By the way, if you are working these out with your calculator, please work these out with your calculator. Make sure they're right. But if you are having a hard time getting your numbers to come out the same as mine or John's, let me know on the video chat or message me ahead of time if you're really annoyed. I know you won't, but pretend. And I'll help you figure it out. This is one of the few times when I'm like, dang it, it would be so much easier if we were together. Okay, one more, and it's shorter like that other one. 3.5. I'm going out the top of the chimney there, aren't I? Okay, last one. If y equals 4,302, find A, log of y, and B, the natural log of y. Okay, this looks weird too, doesn't it? That doesn't look like anything we've seen before. So let me explain what we've got. There's no number here, right? I said here that When we're using base 10, we write the little 10 down here. But here's a shorthand. It's kind of like, you know how when we're taking the square root, we don't put this little number there? We just do it like that. Same thing here. Log 10y, we just don't even take the time because 10 is the most normal. So we just write it as that. So if it helps you to put in a little 10 there, that's fine. And I'll do that in the beginning. Okay? So let's find this. So this is telling me, again, here's my paper. This is telling me the base is 10. So the number written next to it, that's the number. And so John's asking us to find the exponent, right? So we can plug this in here. So we can say log 10, 4,302. So the way we read this is, what is the exponent that we put on 10 to get the number 4,302? And again, so we go here. We know we want the base 10 side, cover that up. We know the number and we need the exponent. So we use this button. And when we plug it in, we get a 3.63. And that tells us that 10 to the 3.63 equals 4,302. And if we really want to be thorough, we can use this button to double check it, right? We can put in 3.63 and then hit this button and we should get this number back. Oh, cool, right? Now, I don't think I explained this before, which is sad, but ln is another way of writing the log of e. Why? Why do mathematicians feel it's necessary to mix things up and make it so crazy? I'm sorry, I don't know. But you can reimagine this as log e of y, if that helps you in the beginning, right? But that explains why these buttons look so different. Because this means log of e, which is equal to that. But we just write natural log. I'm sorry. I blame the scientists. Okay, so let's just think of it like this for this problem. So we're saying the log e y is that. So it's like we were saying over here. This one says, what is the exponent that we put on the base of e, 2.71828, to get 4,302? And another way we could write that, no, that's right, that's what I want to say. Y equals, no, this shouldn't say y. I'm sorry, I shouldn't have written it last time, and I don't want to write it this time. This is the exponent, okay? That's what this equals, okay? What is the exponent we put on 10 to get 4,302? That's the exponent. What is the exponent we put on e to get 4,302? That number is bigger. It's 8.37. So the exponent equals, what did I say, 8.37? Yes, just want to double check. And we can double check that as well by taking the base of e, which again is 2.71828, and raising it to the 8.37 power using this button, right? We would enter 8.37, punch that little bad boy, and then that should give us this number back again. These are the answers that John was looking for in the problem. This is the way we can check our work. I'm not advocating checking your work on an ongoing basis, but if you start to get turned around inside out and upside down, it's a great way to kind of get your feet back on the ground. Okay, I feel like I've probably confused you and made you want to cry and wonder why we couldn't have had 112 lessons of math instead of 113. I know, I'm sorry. But let me just take you back to this. When you just look at this, logarithms are flippin' easy. And everything else is going to make more sense later, trust me. All right, if you can understand this, how I got from here to here, yay. Okay, that's all I have to say. I think I've said quite enough, don't you? Goodbye.